Hi everyone, so today we'll be presenting our presentation, which is about intersection scenario generation for testing autonomous vehicles. I'm Roxana and my teammates are Vedant and Luna. We'll first start by talking about the history of autonomous vehicles. Humans have always had the dream of a smart world with autonomous cars. Driverless cars and taxis were part of science fiction books since 1935. One of the first advertisements about future autonomous vehicles was actually 1950s. Making smart cars is very difficult. Therefore, early driving plans focused on inventing highways that are suited for smart cars. Later in 1950s, the autonomous highway system was invented, which included a radio control for speed and steering. A picture of the highway is shown at the top right corner of our screen. The first autonomous car was created by Japan and it achieved a speed of 20 miles per hour. A picture of the car is shown on the top left corner. The second autonomous vehicle was created by Mercedes in 1986, and they worked on it until 2003. It was called the Dickmans, and by 1993, it was able to go up to 110 miles per hour. Inside of the outside of the car is shown at the bottom of the screen. Today, people can buy self-driving cars from different companies such as Tesla, and self-driving cars have been used in airports such as ones in Dubai. Navia was created in 2014, and it was the first commercially available self-driving car, and it was designed for closed environments. So now we're going to talk about the differences between the driving assistance system, and the autonomous driving system. The driving assistance system is an assistance system that helps the drivers in parking functions and driving. After the driving assistance system, the autonomous driving assistance system was created, which is a support function that helps the driver to safely reach the destination and to avoid accidents. Autonomous driving systems classify the degree of automation with the concept of level. Levels range from 0 to 5, and level 0 includes no assistance and the human is in control of the car, while in level 5, there's total automation, which means there's no need for a human driver. And a picture that talks about the levels in more details is shown at the bottom of our screen. So the ultimate goal of self-driving cars are to avoid accidents and to drive the passenger and the driver safely to the destination. It is shown that 94% of accidents are caused by human errors. So by creating self-driving cars, we can avoid accidents and make sure that the roads are safer for everyone. Self-driving cars are coded to follow instructions and rules of the road, such as stopping at the stop sign. While humans may sometimes break these rules, autonomous vehicles don't. By following these rules, we can make sure that there's less traffic and less accidents. Another goal of self-driving cars are to be fully automated and for there to be no need for human drivers. This matches with the autonomous driving system level 5, which includes no human driver. And lastly, there are other improvements that self-driving car companies have been looking forward to, such as making sure that cars have a high speed. For example, going back to the first autonomous car that was created by Japan, it could go only 20 miles per hour, while the second autonomous car that was created by Mercedes could go up to 110 miles per hour. As we see, the trend is to create vehicles that have high speeds and are self-driven.
So there are many different ways to test autonomous vehicles, and the most popular ways include real-world testing and simulation testing, and other types include formal methods, dynamic testing, hybrid testing, and shadow testing. So some challenges of autonomous vehicle testing include long tail, where usually in the real world, the distribution of possible situations that can arise has a very long tail, meaning that the number of rare situations that the vehicle may encounter is almost unlimited. Another critical difference is that advanced driver systems need to respond safely even in a system failure. Autonomous vehicles need to be fail operational, while advanced driver assistance systems is a fail safe system. The conventional software validation approach uses a requirements traceability matrix for the system level test, but the approach becomes futile in the context of autonomous vehicles because of the use of machine learning techniques, which uses training data instead of a traditional design process. For this reason, it's vital to ensure that training data and testing cover all relevant situations and all operational conditions. And known risks are very rare. These are the risks that an organization is aware of but is disregarding them, either intentionally or unintentionally. Unknown knowns are not acceptable from a risk management perspective. If a risk is known, everything must be done to manage it. So there are advantages when it comes to real world testing in the sense that when it happens in the real world, then you can ensure that as long as the car continues to function, then when the same situation is met, then everybody on the road and in the car will be safe. And some limitations of real world testing include the fact that it's a physical experiment. So that means that there needs to be a lot of effort. And it's also very expensive because there's a lot of scientists that are required and a lot of machinery and just like the whole entire setup in general. And it's also risky because if an accident does happen, then actual people are in danger. Whereas simulation-based testing, the advantages are that you can test specific modules. For example, you may be currently working on the perception module, and you only need to test that section. You don't need to test the whole entire vehicle, like real world testing. And it's cost effective because you're doing it like on your computer or like on a machine. Like it's not actually physical, so it's more cheap than real world testing. However, some limitations of simulation-based testing include the fact that it requires real-world validation because something works in a simulation doesn't necessarily mean that it's going to work in the real world. And also there's limits on the accuracy of modeling of sensors and vehicle dynamics. So for functional scenarios are the highest abstraction level of scenario representation. They can be represented linguistically to ensure human readability. For example, a functional scenario description for a highway pilot can be a truck and a car are driving on the right lane on a 2-lane motorway in a curve where the car follows the truck. And logical scenarios are a detailed representation of functional scenarios with the state space variables. State space variables describe entities and their relations. Logical scenarios provide the parameters and a range of values for each parameter. The range can be discrete or continuous, and concrete scenarios describe the entities and parameters using exact values. Concrete scenarios are the lowest level of abstraction because instead of providing a range like logical scenarios, concrete scenarios provide exact values.
The challenges behind scenario-based testing for autonomous vehicles. So most of the scenarios are unknown. So there are very few scenarios that are known, and when humans create these scenarios manually, they're not able to exhaust the whole space of possible scenarios. This leads to autonomous vehicles not being trained enough to go in the real world and be safe from accidents. Furthermore, because of scenario-based testing, there's a need for real-world validation, and we need to test autonomous vehicles even after testing them on simulation. So one way to handle these challenges is to automate the process of making the scenarios. So there are two processes of making scenarios automatically: scenario extraction and scenario generation. As the name tells you, scenario extraction basically takes data from the real world or simulation and then extracts specific scenarios. So first one is the rare scenario extraction. This extracts just rare or accident scenarios from a lot of data. And then there is representative scenario extraction, which basically clusters every single scenario that there is: safe scenarios, accident scenarios, near accident scenarios. And Then there is scenario generation. Scenario generation can be done using deep learning and a knowledge base. Deep learning uses general adversarial networks and recurrent neural networks to, with the help of real world simulation data, to generate new scenarios that have not occurred before. The other one is to use knowledge base for ontologies. Ontologies are basically rules that define a scenario. A computer can then change or manipulate some of these rules to make new kinds of scenarios that the vehicle may not have encountered before. So what did we do? So our group specifically looked at scenarios on intersections, as intersections are where the most accidents occur. To do this, we used autonomous vehicles simulator called Carla. The autonomous vehicle simulator Carla, we use this because it already has a lot of autonomous vehicle driving modules, and it also manages it. It can also load various types of roads and intersections and any road file that you give it to you. We can also record and replay these scenarios. Um, so what did we do? What did we actually do? So we took an intersection, as you see on the photo right bottom. This is the intersection that we specifically looked at. So we spawned different kinds of vehicles at different points so that we get to see meaningful behavior. Some of these vehicles are aggressive. Some of these vehicles behave cautiously. Some of them behave more normally or like normal human drivers, not aggressive, not too cautious. If you see on the top image, you will see a possible a collision scenario that might occur. The blue car wants to go left, but it's a red car going straight forward. So how do different drivers react to these scenarios? This is what we want to look at. So the results. So I'll show you a video about our results now. Right, there are two vehicles that are going to collide on the left lane. So this is a scenario that we could extract and where we could study aggressive or cautious behavior as it is being deemed. So what could we do in the future with this work? So our aim is to make driver models that accurately imitate humans. The driver models or the autonomous vehicle simulation that we just used usually tend to be not very accident prone, and because in the real world humans make mistakes, most of the accidents occur because of human mistakes, and we need to make models that can make some of these human mistakes at times so that autonomous vehicles are ready to encounter these scenarios in the real world. We would like to thank our wonderful mentor, Abdul Jawad, for guiding us throughout the summer and giving us the right resources to learn and make progress through this research. We are also very grateful to SIP and the whole community for the opportunity to work on this project and participate in the research for the course of the summer. Thank you.